Good evening, ladies and gentlemen. Today we have a question in calculus, rate of the change. The question saying that a laser beam is away from a wall by 150 meters, and as per the figure below, if the rate of the change of the angle theta with respect to the time is 1.5 degree per second, find how fast the beam length change when the beam length L is 170 meters. We show you the most important figure here. So this is the wall we have, and the laser source is here away from the wall by 150 meters. The beam of the laser is here, which is, we named it L, and this is right angle triangle. So the question gave us the rate of the change of the angle with respect to the time, 1.5 degree per second. And the question asking for the dl over dt, which is the how fast the length of the beam will change with the time. In the right angle triangle, we can apply the most important relation, which is Pythagorean. And before we do that, I just want to mention that this side length, which is, I named it x, and if I use the sine of the angle theta, which is equal to the opposite over the hypotenuse, so it's x over L. And if I cross multiply, I can get x equal to L times sine theta. So first thing I'm going to start with is Pythagorean. Pythagorean, according to Pythagorean, the square of the hypotenuse equal to the sum of the square of the other two sides. So the square of the L equal to 150 squared plus x squared. Well, I replaced x by L sine theta, but I'm going to distribute the square for both of them. So I'm going to write down here L squared is equal to 150 squared plus L squared sine squared of theta. The important part now is to take the derivative of this equation, or derivative of L with respect of theta, because I have only two variables. One of them is L, the other one is theta. I don't have anything else. So if I take the derivative here, that's going to be a 2L dl over d theta, that's for the first part, and then derivative of the constant, as you know, it's 0. So there is nothing here. But for this one, since it's a product between two functions, so I am going to apply the product law. The product law is the first times the derivative of the second. So first is L squared times the derivative of sine squared, which is going to be 2 sine theta, and then times cosine theta times 1, because the angle's derivative is 1, and a close bracket there. And then now the second times the derivative of the first, which is sine square of theta times the derivative of L squared, which is going to be 2L dl over d theta. I close this bracket and simplify this equation. So according to this, I will say that 2L dl over d theta, if I move this term also, including dl of d theta, to the other side and organize it a little bit, so I would say that it is minus 2L, because this is positive, but it is a sine square of theta dl over d theta, and I keep this term as it is but organize it a little bit. So it's going to be a 2L squared sine theta cosine theta. That's it. And now I'm going to take, or maybe I can divide both sides by this equation. If I divide this equation by 2L to simplify everything, so I will get here only dl over d theta, and I will get here minus sine square of theta dl of d theta also, and I get here one of the L will go, and then it's just 2L left, and sine theta, or just L left, not 2, because I'm dividing by 2L. So L sine theta cosine theta. Now I'm going to take this as a common factor. So I will say dl over d theta is equal to, or actually, sorry, if I take it as a common factor, I'm going to open a bracket. So it's 1 minus sine square of theta. Here we go. And then we have L sine theta cosine theta. Now I can divide both sides by this bracket to simplify 1 minus sine square of theta, and I will have now a dl over d theta equals to L sine theta cosine theta, all divided by 1 minus sine square of theta. We know from the Pythagorean, also from the relation we have, that sine square of an angle plus the cosine square of the same angle equals to 1. And if I move sine square to the other side, I will get cosine square of theta equals to 1 minus sine square of theta. I replace 1 minus sine square of theta by cosine square of theta. So I'm going to write down here L sine theta cosine theta divided by cosine square of theta. Cancel cosine with the square here. I will get L sine theta over cosine theta, which is actually a tangent theta, which means that I have L tangent theta. I got this in my hand. Now, the last part of this video is to find the rate of the change of the length of the beam with respect to the time. I can combine this rate with the rate given in the question and make them together. So I will say that with respect of d theta multiplied by d theta over dt, because d theta with d theta cancel out each other and I get dl over dt. That's what I need. This part here is given in the question. It's 1.5. And this part, I just got it here. It is an L tangent theta. So now I need to replace all of these things. The L, as the question asking for, is 170. I'm going to substitute 170. And this is 1.5. Close the bracket. The tangent of the angle theta is actually the opposite over adjacent. So I'm going to put x over 150. And I can find simply, if this is 170 and this is 150, if I apply just simply Pythagorean without doing all the details, 170 square equal to 150 square plus x square, I can say very fast x is an 80, and I put 80 instead of x. So 80 divided by 150 multiplied by 1.5 multiplied by 170, the answer is going to be 136 meter per second. That's the rate of the change of the length of the beam with respect to the time. And this is the end of the video. Thank you so much.